but I just want to introduce this material using the PowerPoints, and then we'll move on to the usual kind of exercises and introduction that I usually do when we're doing these sessions. Okay, so let me just click in there so I can go through it. We started to talk about the T distribution last time we were together. This idea that when we calculate confidence intervals, that if we're working with a small sample, that we don't know the population standard deviation. Remember, we don't know sigma. Well, in that situation, that we can't just use the Z value, like for 95% confidence interval, we can't just use 1.96 because when we normally take a sample, we don't know the population mean or the population standard deviation. So the only window that we have onto the population mean and standard deviation is what the distribution of the sample that we see. Okay, so by not knowing what sigma is, we introduce an extra level of uncertainty in guessing what the true population mean is. So that extra level of uncertainty is adjusted for by using a distribution, a normal distribution that's based on different sample sizes. So if the sample size is small, that distribution, while it looks normal, is spread out more than the normal distribution. So 95% of that distribution, middle 95% of that distribution, instead of being at 1.96 standard deviations below the mean and 1.9 standard deviations above the mean, instead of that, it's a bit further out. Like, for instance, it might be 2.1 standard deviations below and above the mean if it's a small sample. If it's an even smaller sample, it might be 2.3. So the distribution is wider. So when we calculate our confidence interval, remember what our confidence interval is based on? Remember how we calculated a confidence interval? We said that our confidence interval for, say, X bar was X bar plus or minus 1.96 times our standard error, right? And our standard error was sigma over the square root of the sample size. Well, now, since we don't know sigma, we have to use the standard deviation of the sample. So our standard error is equal to the standard deviation of the sample of the square root of n. And that gives us that extra level of uncertainty. But we're going to make up for that by, instead of using the Z value for 95% confidence, we're going to use the T distribution value. And we're going to get that from a table. And when we work later on, we'll see that table. And instead, what happens is that number becomes larger than 1.96. Let's say it's 2.2 instead of 1.96. So what does that do to our 95% confidence interval? When we don't know the population sigma, population standard deviation, and we're forced to use the standard deviation of the sample because we're less certain, what is using that T value, 2.2 instead of 1.96, do to our confidence interval? Makes it wider, right? Which makes sense, because in order to make up for that extra level of uncertainty by not knowing what sigma is, we make our confidence interval wider to accommodate that uncertainty and make sure that we really have a 95% chance of capturing the true population mean. Okay, so let me just run through this. Okay, let me just, whoops, pointer, and let me clear this. Okay, so we're okay, here's a picture of our confidence interval. It's X bar plus or minus T. Notice how they use alpha over 2 degrees and then degrees of freedom. What they're saying there, they're describing alpha is the level of uncertainty, the level of error that we're willing to accept. And alpha error is the kind of error where, in this case, is the error where we would miss capturing the mean in our confidence interval. So the level of error we're willing to accept when we have a 95% confidence interval is 5%. What this is saying is alpha over 2. Alpha over 2 means how much of it is in one tail of our distribution. Well, that's 2.5%. So alpha is 2.5. Alpha over 2 is 2.5%. You got 2 tails, so it's 5%. they tend to use that notation alpha over 2 instead of alpha. I'm not sure why we don't just use alpha. I think using alpha would be better, right? A little less confusing, but that's the way they do it. And that comma for degrees of freedom, the degrees of freedom, don't recall exactly how far we got, but the degrees of freedom are related to the sample size. The degrees of freedom are the sample size minus 1. Okay, just to give you an example of how we get to that or how we might interpret that, if I took a sample of 1 from a population, let's say population of all the children in the 6th grade in New York City, and I wanted to know what their average blood sugar level was. If I took a sample of just 1 child, I have some idea maybe what the mean is, not a very good one because it could be high or could be low. But what do I know about the variability? I don't know anything. I only have 1. I don't know. I have no idea if it's 50, next is going to be 500, next one going to be 0. Right? I have nothing and no information about the variability. So I need at least 2 to have any idea about what the variability is. So I could see, oh, that one was 50, this one's 70. At least now I know what the range of this is starting to look like. And the more I sample, the better information I have about the variability, the standard deviation. So 1 basically represents, so 1 really doesn't help us about the variability. 2, we have at least one other value to tell us about the variability. Hence, we call that degrees of freedom. So when we have a sample size of 2, 1 degree of freedom. When we have sample size of 5, 4 degrees of freedom. Okay, so that's kind of like where that comes from. Not entirely, but kind of where that comes from. Okay, so here's what that t distribution looks like. This is what we're going to use when we deal with samples from them. Remember, in the beginning here, as a crutch, we only dealt with populations, right? Because it made it easier. We could use make believe we knew the standard deviation of the population, so we knew what standard error, we knew exactly what it had to be, right? But when we deal with real samples, we're never going to sample the entire population. So we're dealing with different sample sizes. So in this case, whoops. So in this case, okay, here is our sample size, except it's expressed in degrees of freedom, right? So a sample size of 11 would be 10 degrees of freedom, right? N equals 11 is 10 degrees of freedom. And then in order to be able to determine what t value that we need for 95%, in other words, 5% being in one tail, 5% being in the other tail, right? 5% in this tail, 5%. And then in order to be able to know what z-score to use for all these different sample sizes, for every different sample size, we would need a t-table for every one of these sample sizes. Well, rather than bother with that, we're really only usually interested in what the t-score and z-score has to be for 95%, 90%, and 99%. The rest of them, we really probably are not going to be that concerned about, except when we were doing our initial exercises with areas of the distribution. So really, we're really mostly just interested in, let's see, 2 tails. Okay, 1 tail, 2 tails, 5%. This is the 95% confidence interval, right? So if you'll notice that if I have 10 degrees, if I have a 10 degrees of freedom, a sample size of 11, the value that I need to use for t is 2.23. Okay, it's kind of hard to see there, right? Okay, I can't get it to expand without dropping out. Oh, maybe I can. I'll leave that there. I'll read them to you at any rate. So 2.23. If my sample size is 20, the t value is 2.09. Well, why is that? Why is it 2.09 instead of 2.23? Well, what's happened here is since I have a bigger sample, it's not cooperating. Since I have a bigger sample, I'm gonna have to point at it differently. Okay, or let's go down here. Since I have a bigger sample, 2.09, a sample size of 21, 20 degrees of freedom. So that big a sample, I have a better idea what the true sigma is of the population. My standard deviation from my sample of size 20 gives me a better idea what the variability is. So my margin of error can be smaller and my t-score can be smaller. So now I would use 2.09. If I had a really super big sample, 100 people, well, look what happens to the value of t. It gets closer and closer to 1.96, right? If we sampled everybody in the population, it would be 1.96, right? Usually when the sample size gets very large, like say 100, right? A lot of times we'll just say, well, why even bother with all this? Why not just use 1.96, right? So, I'm sorry? To be completely correct, you would have to sample the whole population before you use 1.96, because you need to know what sigma is to use 1.96. However, in practical reality, if we have a sample size of 100, we're saying that the standard deviation is such a good representation of sigma of those 100 people. The standard deviation of those 100 people is such a good estimate of what sigma is that we're just going to call it 1.96. In fact, if you use the t-table, I wouldn't be surprised if the t-table told you 1.97 or 1.98, something like that. So it's so close that a lot of textbooks will tell you that over a sample size of such and such, just use 1.96. That's the reasoning, is that it's just easy to do, right? But in reality, you would have to know the whole population to really do that. In fact, SPSS, when we use SPSS, it calculates the t-value for any sample size, whether it's 100, 1,000, it doesn't care. It calculates the t-value and uses that. It never uses 1.96 because everything it does is based on a sample, right? So when you use software like SPSS, you don't even worry about that because it's going to use the value that's appropriate for that sample size. Okay, so let me move on from here. Okay, so just as kind of as an introduction, okay, let me get clicked in here and get back to this. Okay, so now we're going to start looking at something called hypothesis testing. Okay, and in hypothesis testing, we are going to evaluate statements about certain kinds of how we can use statistics to allow us to say certain things about certain populations. For instance, if we're dealing with numerical variables, we want to know whether, say, the mean value for population B is equal to the mean value for population A. So we want to set up a hypothesis where we make a hypothesis about them being the same and maybe try and prove that, try and use statistics to prove to a high level of confidence that indeed they're different. So we're answering a yes or no question. Is the mean of this population equal to the mean of this population? Is the proportion of people in this population that have diabetes equal to the proportion of people in this population that have diabetes? Is the blood pressure of people that take this drug lower than the blood pressure of the people that take the placebo? Right? So we need to know that. We really want to know if the whole population took that drug, right? But we're really dealing with a sample. We're not going to give the drug to the entire population to test it. We're going to give it to a sample of people to test it. But we want to know whether the difference that we get between the means for the drug and the placebo, whether they're different enough in the sample to generalize to the entire population. Okay, so that's what hypothesis testing really is all about. Okay, so we have type 1 and type 2 errors, right? So type 1 error is a false positive. In other words, when I say that the mean for group A is different from the mean for group B, and in fact, they aren't different, they're the same. So if I did that so in this case, that's a real problem. Like for instance, this guy, he's telling him that this guy's pregnant. That's a problem, right? So that's a big error. right? So similarly in statistics, a type 1 error is considered a big error, right? And a big error is a situation, let's say I just described to you, that we want to know whether a drug works. And we're comparing the blood pressure of people that took the drug, blood pressure of the people that didn't take the drug. Okay, so now what if I do what if I predict that indeed, oh, they're different. My statistics tells me that they're different. What's going to happen? People are going to use that drug, right? They're going to spend money on it. They're going to take this drug. They're going to have side effects and so on and so forth. What if that's not true? The drug did not lower blood pressure. The blood pressure of the population really is the same as people that took the placebo. But we just predicted it was going to be different. That's a big problem. Oops, let me get this to silence. I have no idea why it's doing that. Oh my goodness, I got the wrong phone. Mike, shit. Excuse me, I got to pause. I have to pause because I got to get Mike.
This
Okay, let me
conference
resume
will now
recording.
be
Sorry,
recorded.
guys. I accidentally, in the last class, I accidentally took my lab assistant's phone instead of my own, and it started alerting there. So I had to make a run down there to make sure I caught him before he left the building. So let me pick up where I was before. So type 1 error is a serious error. That's a problem. That means that we're saying that two means are different. This population is different from that population. And we're going to act on that. We're going to expend public health dollars. We're going to do stuff. People are going to be using drugs that we're approving and so on because we think they're going to improve their blood pressure, when in fact they're not. They're not different. They're the same. And we mistakenly said that they were different. That's a false positive. And that's a type 1 error. A type 2 error is when we have a false negative. In other words, let's say that we say that there's no difference between the placebo and the drug. Okay, what's going to happen there? Well, what's going to happen there is that, well, nobody's going to spend money on that drug. We're not going to use that drug. If it looks promising, we might do a study with a bigger sample size or something like that, but that's a less serious problem than saying something is truly different and then acting on it, right? So that's a type 1 error versus a type 2 error. So our type 1 error that we're willing to accept usually is 5%. So in other words, our confidence interval was 95%, 5% chance that we would miss the true mean. And our level of error for judging our hypothesis that two populations are different is also, say, 5%. Often. Sometimes we want to be more accurate. Sometimes we will be less chance of being wrong, but it's pretty typical. Okay. So, remember I think we started talking about the idea that our confidence interval suggests that that theoretically, that when we take a sample, 95% of those sample results are going to be within this range, 1.96 standard deviations, and 1.96 standard deviations above and below the mean that we get for all of our sample means. 95% of the time, the mean of all our samples is going to be here, and 95% of additional samples we take are going to be within this range of the true mean for our samples and for the population as well. Okay, so very frequently what we'll say is that maybe I can say to myself, well, here's my range for my population mean. Here's what my sample was, and that tells me that I'm 90% sure, 95% sure that my true mean for my population is between 90 and 110, let's say, right? So if I know another population's mean, if I know the mean of some other population is equal to 85, I might be tempted to say to myself that since I know with 95% certainty that the mean for population A is between these two numbers and the known mean for population B is 85, I might be inclined to say that the mean for population A, which we really don't know, we just know the range, we just suspect we know the range with that level of certainty, that I might be willing to say with 95% certainty that the mean for population B and the mean for population A are different, right? Makes sense, right? So actually, that's not a bad way to look at this. However, things get a little bit more complicated when we look at samples from two populations. So like in other words, let's say that we find that group A, we take a sample and we find that the population mean for group A, based on our sample, that our mean is here for our sample, and our confidence interval for A is 80 to 100, right? We're 95% sure that the mean for group A is between those two numbers. And then on the other hand, for group B, I take a sample and I find that my confidence interval is, let's say, 60 to 75, right? So now I'm 95% sure the mean for population B is between these two numbers, and I'm 95% sure the mean for population B, A, is between these two numbers. Can I say I'm 95% sure that the mean for group A is different than the mean for population B? They don't overlap, so it seems like that would be a reasonable thing to do. Well, we can kind of support this, right? But this gets a little tenuous, right? There could be a lot of other stuff going on here. Like, for instance, they could have different variabilities, these two groups. So we don't need it anyway, I don't think. Lights went out, but we don't need them. Okay, so unless you guys, if you need it to read your stuff, so you can just stand up and it'll go back on. Okay, so anyway, we're tempted to do it this way, but when we're dealing with two samples, right, we really have to evaluate how the differences in the variability affect both of these samples. Okay, and whether or not we can consider that the variability of the two samples is the same, is different, if we can pool them, and so on and so forth. So this situation here is what we call a single sample t-test, right? When we do this hypothesis, we set up this hypothesis and test this notion of the means of the two groups being the same or different. In this case, we're doing a single sample t-test. This is a sample. This result is based on a sample. This is a known mean. There's only one sample going on there. This result is two samples. Each sample has its own mean. Each sample has its own variability, its own standard deviation, and so on and so forth. Makes it a little bit more difficult for us to compare the two of them than just looking at the confidence interval for one of the two groups. Okay, so we're gonna find another way to do that. Oops. Okay. And the way that we're going to do that, let me just also, I have another slide group here that I want to look at also. So you want to see where this other one picks up. I'm going to move over to this one because it gives a little bit more background on this idea of the t-test. Okay, so actually, no, I'm going to stick with the first. I'll tough it out with the first one. Okay, so in order to compare means, or proportions. Okay, and this will wind up going on to other kinds of statistics as well. I'm going to formulate a hypothesis. I'm going to state in advance what I'm trying to prove, what I'm trying to, what I think, excuse me, what I think the null condition is, what I think is not true, and what I'm trying to reject that in favor of, what I'm trying to prove. The alternative hypothesis, we're going to set up a null and alternative hypothesis. The alternative hypothesis is the one that's really interesting to us. It states that there's an actual difference between the mean for group A and the mean for group B, right? That's what we want to prove, okay? But the way we do that is that instead of looking at the null and the alternative, instead of looking at just an alternative hypothesis, what we want to prove, we also establish a null hypothesis. In other words, we say that our assumption in this hypothesis is that there's no difference between the two groups. We want to then collect enough evidence and statistics to say with a certain level of certainty, well, the null hypothesis is false, and instead the alternative hypothesis is true. So in each case, we set up a null hypothesis and we set up an alternative hypothesis. So let's take a look at this case. Okay, this is called a two-sided hypothesis. Don't worry about the term two-sided. We'll get to that in a little while. But basically, we're saying that the mean is equal that one mean is equal to a certain value, and the alternative hypothesis is that the mean is not equal to that value. So an example is blood pressure of smoking males in the general population. Our null hypothesis is that the mean is equal to 211, and our alternative hypothesis is that it's different than 211. It's not equal to 211. It's not saying that it's lower. It's not saying that it's higher. It's only saying that it's different. Okay, so we can also do that with proportions. Proportions of one group is equal to proportions of the other group is our null hypothesis. No difference in the prevalence in this case. Proportion represented prevalence. And our alternative hypothesis is that there is a difference in the prevalence of anemia in school children. Okay, we can also have one-sided hypothesis. And one-sided hypothesis, looking at the alternative hypothesis start. The alternative hypothesis says that that our mean is greater than the mean of the other group. Mean of group A is greater than the mean of group B. Okay, that's one-sided because you're saying that we don't care if it's different, if it's lower, but we're interested in proving that it's higher only. Okay, so our null hypothesis is that the mean of the first group is equal to the mean of the second group or is less than the mean of the second group, right? In other words, it could be same or less than. The alternative hypothesis is can only be greater than. Okay, so in order to accept the alternative hypothesis, we have to have enough evidence to reject the null hypothesis, which says it's equal to or less than. Okay, most of the time, we're going to be looking at two-sided hypothesis. Why would we be looking at one-sided hypothesis? We might be looking at one-sided hypothesis when we understood, or if we had knowledge, that the difference between the two populations could only be one direction. This population can only be greater than the other population. No chance of it being less than, right? So the problem with that is that how do you get evidence for that? How can you be sure that if you don't already know what the means are? Okay, well, for instance, you might be testing a drug, which is a vasodilator. Because a vasodilator relaxes blood vessels, right? So you might argue, well, I'm gonna test this drug against a placebo, and I might make this a one-sided test. And the reason why I might make it a one-sided test is because it's a vasodilator and the way it works, it can't increase blood pressure. It can only decrease blood pressure. Question is whether it will decrease blood pressure. So I'm going to do a one-sided test and say my alternative hypothesis is that the blood pressure with the drug is less than the blood pressure without the drug. My null hypothesis is that it's less than or the same as the placebo, right? So that would be an example of a one-sided alternative. We don't do that much because a two-sided hypothesis, number one, is more conservative. It's harder to prove and better in terms of like not making a type 1 error. And often, we very rarely have the evidence that we need to justify making a one-sided hypothesis. Okay, so when we test the hypothesis, what are we doing? We're comparing two means. So in this case, the example that I have here, what we're looking at is we're interested in how far apart these two means are. So if I have a one sample test, okay, what did I say one sample test was? I knew what the mean of group A was, right? And I wanted to compare it to the mean of group B, but I don't really know the mean of group B. I only know the mean of my sample, right? So I want to know how far apart the mean of my sample is from the mean of the other population. Okay, remember before when I did a one sample test, I compared my confidence interval to the mean of that other population, right? In this case, what we're going to do is that instead of doing that, we're going to do something that's a little bit easier, a little bit better to justify. We're going to compare the difference between the mean of our sample and the mean of the other population. And we're going to put it over sigma over the square root of n. Okay, that's called a one sample z-test. What is sigma over the square root of n? That's the standard error. So what I'm calculating here is how many standard errors apart is x bar from mu, right? The mean of one population, mean of the other population. And then I'm going to say to myself, well, if I want to have less than 5% chance of creating an alpha error, of being wrong when I say that they're different, I have to say to myself, well, that z-score needs to be at least, what do you think, what value would I need to be in order to 1.96, right? Okay, and that's if I have a very, very big sample, right? Because in order to justify using 1.96, I need a very large sample. But if I have a normal size sample or a small sample, right? Well, now that z-score, instead of calling it a z-score, I'm going to call it a t-score. And that t-score is not 1.96 anymore. That t-score depends on the sample size. The sample size is going to determine how big this difference has to be in order for you to reject the null hypothesis. So if I have a sample size of 11, you remember we looked at it on the chart, we need that difference to be 2.2 standard errors apart or more in order to say that they're different enough to be 95% sure that the mean of group A is not equal to the mean of group B. Okay? So that t-score now that we looked at before that we were going to use for the confidence intervals, now we're going to use that t-score to determine whether we can reject the null hypothesis that they're the same and accept the alternative hypothesis that they're different. So that t-score now gives us as an additional application. So what I'm going to do is from now on, I'm going to refer to the t-score that I need to be far enough apart to reject the null hypothesis. I'm going to call that from now on t-critical. And where do I find out what t-critical is? T-critical is only based on the sample size, right? Once you know the sample size, you go to that table, look up what the t-score is. Maybe it's 2.05, right? For a sample size of say 25, right? And that from that point on, you're going to say t-critical is 2.05 for that sample size. And now when you calculate your t-value, when you look at the difference between the two means, your sample mean and the other population mean, and put it over the standard error, you need that to be at least 2.05 standard errors apart in order to reject your null hypothesis and accept your alternative hypothesis. It's going to get simpler in practice, trust me. Okay. Oops. I'm gonna bust through this quickly now. Okay. Okay. I'm not going to talk about the p-value right now. We'll talk about that later. Okay. Now, we also have situations where instead of dealing with a one mean, we're dealing with two means. I'll put up the recording of this that Levi did, so you can go through the rest of this presentation.
I don't know.
Yes.
One side versus
Two-sided. I'll get to that. I'll explain that in my words, and then you can hear the more complicated real version. Okay. I'll give you an interpretive version of it, and then I'll make sure that a full recording of the presentation is available. Okay. So now where did all this come from? What is the origin of all this stuff? Okay, a fellow by the name of William Gossett worked for a brewery, worked for Guinness, in fact. And Guinness is famous for being very precise in its formulas having calculated very carefully how to produce its various ales and so on and so forth. And he worked as a chemist for them, as a biologist and a chemist. And he was responsible for testing the batches of beer, quality control, making sure everything was exactly the same, and so on and so forth. So very frequently, when he would test batches of beer, he would not be able to take 100 samples. He would have to work with relatively small sample sizes, right? Like he'd have 4 samples from this batch and 7 samples from this batch, and so on and so forth. So sampling variability in small batches is a problem because you only know so much about how variable what really the value is from the variability in a small sample. So he developed this idea of a t-distribution and what's called a student's t-test. He published his work because his employer probably would not have let him publish this material under his own name while he was working with them. He published it under the pseudonym student. Okay, and not actual student, but that was the name that he used. So these t-distributions and this idea of a t-test in place of the z-value to accommodate for the variability that is inevitably introduced, the increased variability is inevitably introduced by using small samples, is an adjustment for that problem. So anytime we're dealing with samples now, we use the t-distribution instead of the z distribution. And so the standard error we're going to calculate as being equal to standard deviation over the square root of n. Okay. Okay. And if assuming that that a sample is drawn from a normally distributed population, then the t-test formula, the formula for the t-test is x bar minus the mean that we're comparing it to over the standard error. Standard error being defined by the standard deviation of the sample. Remember, it's a small sample, so that can be very variable over the square root of n. Okay, and we describe the t-distribution having a degrees of freedom that's equal to n minus 1. Okay, now the higher the degrees of freedom, the closer, in other words, same thing as saying higher the sample size, the closer the t-distribution is to the standard normal distribution, that 1.96. Okay, and here's the tables based on that. Okay, let me get into some examples. Oops. Okay. Oh, come on, open up. Here we go. Okay, I don't want to do that right now. I'll get into the next one. Okay, so let's take a look at how we might set up a specific problem using hypothesis testing. Okay, so in this case, the mean SAT scores for a population of first-year students at Hunter is 620. The standard deviations of scores in this population is known to be 95. Now, okay, so the mean SAT score for first-year students is 620. The standard deviation of scores in this population is known to be 95. Investigator believes that the mean SAT score of first-year psychology majors is significantly different than the mean score of the population. The mean of a sample 36 randomly selected psychology majors is 648. Test the above claim using a 95% confidence interval and a single sample hypothesis test. Alpha, in other words, alpha is equal to 0.05. We're willing to accept a 5% chance of being wrong, a type 1 error, rejecting the null hypothesis when we shouldn't. So what do we know here? We know that the population of students at Hunter, first year population of students, mu is equal to 620, and the standard deviation is equal to 95. We know both of those because we've measured, we have the scores for all of the students. Now, the problem here is that we're going to compare them to psychology majors, but we don't have that data separately. So we got that data by sampling 36 students, right? And we found that the mean for those students is 648. And we say to ourselves, okay, mean 648, sample size is 36. Is this mu or is this X bar, 648? Right, because it's the sample mean, right? So I'm going to assume that the standard deviations of these groups is same, standard deviation is 95, and that we know the standard deviation. So what is our null and alternative hypothesis when we compare these two means? We're saying our null hypothesis is that mu for all students is equal to mu for the psychology students, right? What's our alternative hypothesis? Yeah. Now, when we set up we're going to be comparing X bar to the mean for the population. But when we set up our null and alternative hypothesis, we always talk about the means, right? Mean 1 is equal to mean 2. Mean 1 is not equal to 2, right? This is a two-sided hypothesis. We're not predicting ahead of time whether one is larger than the other. We're just trying to predict whether they're different, right? So we didn't put a less than or greater than in the alternative. So our alternative hypothesis is that they're not the same, that the means are not the same. So now I'm going to calculate the standard error. So my standard error for that sample size is going to be, and because we know we're assuming that the standard deviation for the population is the same, because we didn't get a separate one. So the only thing we have is to assume that it's the same, is sigma over the square root of n, okay, which is 95 over the square root of the sample size, which was 36, which is 6. So 6 into 95. Oops, I take out my contacts. I didn't need that. 15.8, good, okay. Okay, equals 15.8, right? So now 15.8, so now we're going to take a look at how far apart are these two means. So our difference is going to be, what is our difference going to be? Let's see. It's going to be, now first of all, should I use Z or T here? The sample was 36, but what did we say we knew?
Sorry, standard.
Right, so if we know the standard deviation, we're assuming it's the same as the population standard deviation. I'm going to use Z, right? So Z is going to be equal to the difference between the two means, which is 620 minus 640. I'm sorry, I'm going to use the first one. X is going to be X bar minus mu over the standard error is equal to 648 minus 620 over 15.8. Can we figure that out for me? In the meantime, let me get my pointer so I can get this out of the way. Okay, what does that come out to? 28 over 15.8.
I would say 1.8.
What?
I approximate 1.77.
1.77. Okay, so our Z value is 1.77. In order to be 95% sure, in other words, less than 5% chance of being wrong, how far apart, how many Z scores, how many standard errors apart do we need these two means to be? We need Z to be 1.96 or greater, equal to or greater than 1.96. Is it greater than 1.96? No. So these means are not far enough apart for us to reject the null hypothesis and accept the alternative hypothesis. So what do we say in this case? We say simply that we fail to reject the null hypothesis. Let me get this to scroll up.
Can you repeat that phrase? These means are not far enough.
I'm going to be doing it a few times. Okay, so. Okay, calculate standard error, carry good productivity Z-test. Z-test in this case, state your conclusions. Okay, let's take the next one. It's mean, look, it's remarkably similar. Okay. Okay. Okay, so we got the same sample. In this one, the only difference is the sample size, right? Let's go ahead and do it. What the hell? Again, we know what the standard deviation is, 95, right? So it's going to be a Z-score. So a null hypothesis is that the mean for all majors is equal to the mean for psych majors, and an alternative hypothesis, the mean for all majors is not equal to the mean for psych majors. Okay, calculate our standard error. Our standard error is equal to sigma over the square root of the sample size is equal to 95 over 25 over the square root of 25 is equal to 5 into 95 is 119, right?
Yes.
Okay, good. So standard error is equal to 19. So now we have to say to ourselves, okay, so calculate the appropriate test Z or T. Since we know sigma, since we know what sigma is, we're going to use Z. So Z is equal to X bar minus mu over the standard error. Okay, number of standard errors apart is what we're after. Z is equal to 620, 648 was the same numbers. Yeah, 28 over 19. That's even smaller. That's maybe just 1.4. So again, we failed to reject the null hypothesis. You know, I bet you the one before this, I probably was looking for a bigger difference. Should have been a bigger difference so that we could reject one. That's okay. So we get the same result. We need that to be bigger than 1.96 to make sure they're far enough apart to be 95% certain, less than 5% chance of being wrong. Okay, hopefully I get an interesting result out of the next one. And let me just get to the pointer. Okay, good. Okay, mean number of close friends for a population of people living in New York is 5.7. The standard deviation is up. Another one with population. I want to get the one without a population. Dun, dun, dun. Scores in this population 1.3. Mean number of close friends population. Let's see if we get something better. No, Let me try a different one. Okay, let's take a look at this one. I'm taking sample. This might be any kind of situation where I might be involved in sampling from a population, taking a survey or something like that. And I'm going to compare this. We're going to take a sample. This is a sample. Whoops, let me get a pen. This is a sample from a group, say population A. And we're comparing it to a known mean from population B. Do I know the standard deviation? Do I know sigma for either one of these populations? No, I don't, right? So how am I going to, oh, wait a second, I said I know sigma there. Okay, let's say that we know, in this one, we know what sigma is. Excuse me, I get what I'm doing here. This one, we know sigma is equal to 3. We're told that the population standard deviation for population is equal to 3. So this allows us to use the Z table instead of the T table. So let's do that. So in other words, in this problem, I can say to myself, let's take the average of these numbers. And I don't have Excel handy, right? I was actually going to type it into Excel. Oops, I got to change this to a pointer. Matter of fact, I'll bet you. I was also would be surprised if whoops. Okay, the average of these numbers is 9.89 something or other. Okay. Let me just make sure I got that number. I'm just going to call that 9.9. Okay, the average is X bar. Get my pen back. X bar is equal to 9.9. Okay, my sample size is 9. Standard deviation of my population A is 3. So if I wanted to know, if I set up a hypothesis test here, what would my hypothesis test look like? Well, first thing I would say is the mean for population A is equal to the mean for population B. That's my null hypothesis, H null. My alternative hypothesis would be the mean for population A is not equal to the mean for population B. Okay, so now I want to go ahead and prove that. So to prove that, I'm going to try and show that my mean of 9.9 is different enough from my known mean for this other population that I can say with 95% certainty that the true population of mean A is not the same as the true population of mean B. So how am I going to do that? Well, I'm going to use my t-test. In this case, I know sigma, so I'm just going to use Z instead. So Z is equal to X bar, the mean for population A, minus the mean for population B. I'm putting mu in there because I know what it is, divided by the standard error. So what's my standard error going to be? It's going to be equal to 3 divided by the square root of 9, which is 3. So this is going to be equal to 9.9 divided by 3. So that's going to be equal to 3.3. Okay, look right? That looks right to me. Okay, so now what is the critical value of Z that I have to exceed in order to be 95% sure that these means are far enough apart? The critical value of Z has to be equal to 1.96. Have I exceeded the critical value of Z? So what can I say about my null and alternative hypothesis? I can
Except,
reject my null hypothesis and accept my alternative hypothesis. Okay, so what are our choices here when we come to that point? One choice is that if they're not far enough apart, then I would say I fail to reject my null hypothesis. The other choice that I have is I reject my null hypothesis and I accept my alternative hypothesis. Okay, well, let's say if this had come out to 1.5 instead of 3.3, could I say I accept my null hypothesis?
no, you
Say you
reject.
fail.
Yeah, I just say I fail to reject the null hypothesis. Why is that? Because I haven't proved that this is true. All I've done is I don't have enough evidence to say that they're different. This test is not geared to to proving that they're equal. It's geared to proving that they're different. So when you fail that, you can't just say they're the same. You can only say you failed to reject the null hypothesis. Okay, so let's take a look at this. If we hadn't known what sigma was, okay, so how would this look if we hadn't known what sigma was? If we hadn't known what sigma was, when we worked with Excel, we would have calculated our standard deviation from Excel, from that sample. Okay, so what's our standard deviation equal to? It's equal to standard deviation, parentheses. I know you guys can't see this. I'm just trying to get through it quickly. And the standard deviation is equal to 2.93, almost the same thing. Okay, so I'm going to say that it's 2.93, and effectively it's almost the same thing anyway. However, 2.93, now it's not sigma, but standard deviation is equal to 2.93. Okay, so now when I do my test now, what am I going to use? Am I going to use Z? I'm going to use T instead. T is equal to X bar minus mu for group B over the standard deviation divided by the square root of n, right? So what's that going to be equal? That's going to be equal to, the difference is the same as before, which was 9.9 divided by standard deviation is equal to 2.93, right? So it comes out to basically around the same thing, 3.3. Except this time, I don't compare it to Z is equal to 1.96. What do I compare it to? I compare it to my critical value of T. So how do I get my critical value of T? You got it, exactly. Let me go up there and get it. Okay, Agresti T, and you can use the one in your book. You don't have to use this one. Here's the Agresti T table. So what was our sample size? Our sample size was 9, right? So let's take a look at how many degrees of freedom is that? That's 8 degrees of freedom. Here's our 95% confidence interval. T over T for the right tail probability is 0.025, 2.5%, which means an alpha of 0.5% if you do a two-sided test. 2.5% chance of being wrong on outside to one side, 2.5% being wrong on the other side. You know how we prevent that? That you can actually turn the switch on manually. That's what we didn't do when we came in, but that's okay. Don't worry about it. Okay. So where were we again? So 8 degrees of freedom. So our T-score for 95% confidence, in other words, alpha is equal to 2 times this, which is 0.05. Alpha 0.05 is 2.306. So T critical is equal to 2.306. Oops. 2.306. So can I reject my null hypothesis? What did T come out to
Oh,
be?
yeah.
I can reject my null hypothesis
That's alternative.
and accept my alternative hypothesis. Maybe the next example will have I don't know why, sometimes I change these. I alter these as I'm working and in classes, and maybe the last time I changed these numbers a couple of times because I'm hoping I want to get one where we can really reject it. Let's see what the next one looks like. Okay, now this one's interesting. What do we have here? We have another problem here. This one is a two sample test. Well, let's see. In other words, we have a X bar for one group and we have X bar for the second group. We don't know either population value, right? So in that case, we can go to Excel. We can import this information to Excel. I'm going to do it for a second here. I'll blow this up so we can actually see it this time. Okay, and I'm going to paste that in here. Okay, here are our two groups, right? Okay, so the mean of this group is equal to this. And the mean of this group, actually, I could just copy this over. Oops. The mean of this group is equal to 7.5. Okay, so now what about standard deviations? Standard deviation of this sample is 2.7, and the standard deviation of this sample, the other sample, group B, is 1.943. Okay, so now I want to compare the two means. So how might I approach that? Well, the way I might approach that is the way that I might approach that is I might say that, let's see, well, first of all, do I know the population standard deviations? No, I don't, right? All I know is the standard deviation from the sample, right? I don't know what sigma is for either one of these two populations. So I know I'm going to be using the t-test, right? So t is equal to x bar for group, I'm going to call this group A, and population B, x bar for population A minus, well, I don't know mu for the other population. All I know is x bar for the other population also, x bar for population B, over the standard error. Oh, okay, standard error. Now, what's the standard error going to be equal to? Standard error is going to be equal to the standard deviation instead of standard error over the square root of the sample size. Well, should I use 2.73? Should I use 1.93? Should I combine? What should I do with that? I have a problem. When I get away from one sample, I now have a situation where I have variability for one group and variability for another group. So I have a couple of choices here. One is I could use this variability. I could use this variability. I could combine the two variables, two variabilities. I can combine all these numbers and find a single standard deviation based on 18 numbers instead of based on 9 numbers, and use the same one for both of them. Well, that seems rational if they're close. If this one was 2.1 and this one was 2.2, they're not that far apart, but they're not close either. So I may say to myself, well, I really can't just combine them. Maybe I can make a weighted average of the two. Maybe there's some other way I can handle it. It gets complicated. Single sample, simple. Two samples, a little bit more complicated, right? One of the possibilities is that the variances are equal, and the other one is that the variances are not equal, and we handle them differently. We're not going to handle them during this session. This session, we're only going to deal with single sample t-tests to keep things a little bit easier for now. But next week, we're going to take a look at two sample t-tests, which is really what in the real world that, well, no, I shouldn't say that. You do the video with single sample t-tests pretty frequently, but in the real world, it's a bit more common to deal with. Okay, I don't want to say. Okay, let me turn this off here. Let me get this out of my way. This was population. I don't like these single sample t-tests. I'm not in love with these examples. We can find some others here. I might have had some from last week that we didn't get to. Well, I can't find it quickly. Nope, same one there. I'm gonna have to do this on the fly, make something up. Okay, I'm gonna give you a couple of hypotheses, simple situations. Okay, let's say that we have, okay, let's say that we sample, we have a sample size of 25. We sample 25 children from elementary schools in the Bronx, and we find that those 25 children have a mean blood lead level of 6 micrograms of lead per deciliter of blood. And we find that we happen to know in a large study that we've done before among New York City schools children that the standard deviation we targeted these 25 kids because they were in schools that were older than a certain number of years old. And that we suspected that their blood lead levels would be more than children in the rest of the city. Now, we know that the standard deviation, the variability in blood lead levels in the rest of the city is equal to, um, um, let's say, 5, 5 micrograms per deciliter. That's the standard deviation for the rest of the city. Now, I want to know what's a 95% confidence interval for the true blood lead levels of children that were in the population that this group was drawn from, right? In other words, Bronx, older schools. Okay, so how am I going to calculate that? Well, I'm looking for 95% confidence interval, so I know it's going to be X bar I'm going to start out with. And I know that's 6 micrograms. And I'm going to say plus or minus, right? And if I'm looking for a 95% confidence interval, right? Again, the notation that they use in the text, alpha over 2. How many degrees of freedom? 24 degrees of freedom, right? And alpha would be 5%, right? So plus or minus, X bar plus or minus, and would I use a T-score here or a Z-score? What was that?
Z.
Okay, I would use a Z-score because I'm assuming that standard deviation is known, right? Okay, which is plus or minus, right? The Z-score times the standard error, right? That's a confidence interval.
Okay.
Okay, so what is it going to be? It's going to be equal to X bar plus or minus, what's the Z-score for 95%? Actually, this should be on there, huh? 1.96 times our standard error. Okay, so X is 6 plus or minus 1.96 times our standard error. Our standard error is equal to sigma over the square root of n, which is equal to 5 over square root of 25 is 5, is equal to 1. So times 1. So what's our 95% confidence interval? It's going to be 4.04 to 6, 8, 7, 7.96, right? That's our 95% confidence interval. Okay, I'm going to do it again, except this time, I don't know what the population standard deviation is. This time, my sample size is going to be 25. Sample size is going to be 25. Our mean, again, is going to be the same. It's going to be equal for those 25 kids. It's going to be 6 micrograms per deciliter. Okay, our population, okay, so our 95% confidence interval, we don't know what sigma is, but we know that the standard deviation for the children in this study was equal to, let's say, what did I say before? 5. I'll say it's the same thing, 5 micrograms per deciliter. So how am I going to, what's this confidence interval going to be? Remember before it was 4.04 to 5, excuse me, 7.96. Okay? So now it's going to be, again, confidence interval. It's going to be X bar plus or minus Z. Z for alpha is equal, alpha over 2 is 2.5%. Okay, and for degrees of freedom, 24, same as before, except that we can't use Z here, can we? It's going to be T for those conditions times the standard error. Okay, so we're going to be 6 plus or minus. The standard error was 6. It was standard error is going to be equal to the standard deviation over the square root of n, right? Because that's all we have to estimate it from, is going to be equal to 5 over the square root of 25, which is 5. It's going to be equal to 1. So it's still going to be equal to 1. But now what's the t-score going to be equal to? We have to get that from the table. So let's go to the table, and our z-score, our z-score for sample size 24 degrees of freedom is going to be equal to 2 point, exactly, good, 2.064. Oops, I'm drifting. Okay, 2.2. Oh my goodness, what happened here? 2.06, not let me draw. And that's working. Why did this happen? Am I doing something? Did I touch something here? I'm going to have to use this. I'm going to have to use a cursor. Times 2.064, right? So now our 95% confidence interval is going to be equal to 6 plus 2.0 minus 2.064 is 3.96. 3.9. 3.94 to 8.06. Right? I'm dropping off the last digit. And what's happened to our confidence interval? It's become wider. And why has it become wider? It's become wider because we had to use the t-value instead of the z-value because we're dealing with the standard deviation from a sample rather than from the population. Okay, now let's apply this to a problem where we do a hypothesis test. Okay. Now, I want to see if I can't get this to work properly. Oops, what happened there? Still only let me draw straight lines. I'm not sure why that's happening. How about here? I'm going to use a highlighter. Nope, still doing that same thing. Let me turn it off, turn it on again. For some reason, it's not obeying my commands. Okay. All right, let me do the best I can with the trackpad. Okay, so I'm gonna now do another version of this. I'm gonna say to myself X bar, wrong pen, X bar. Okay, you can take a sample of size 25. Right, and I'm going to say that X bar, let's see, X bar is equal to 6 again. Okay, my sample size is 25. My standard deviation is equal to, let's see, I think what I got before. Standard deviation is equal to 5 as before. Actually, I'm going to say we're going to use the standard deviation for the population, assume it's the same. It's going to be equal to 5. Okay, and I'm going to compare this to a known population, the known mu for the entire school population, not just the Bronx. This is the Bronx. For the entire school population, the known mean is equal to 8 micrograms per deciliter. Okay, so now I'm going to set up a hypothesis test for our analysis. We know that the entire population of children of that age in New York City has an average blood lead level. I should have gone the other direction. I'm going to call it 4 because it would probably be lower. Okay. 4 micrograms per deciliter. But I took a sample of 25 students from this one specific area I'm concerned about in the Bronx. The sample size was 25. And I want to know whether I can say that the mean for children in the Bronx is different than the mean for children in the rest of the city. Okay, all, so mu all. So what's my null hypothesis going to look like here? My null hypothesis is going to look like that the mean, remember I only use mu for the null hypothesis, the alternative hypothesis. H null, H0, H null is mu for the Bronx is equal to mu for all. And my alternative hypothesis is H alternative.
Mu for the Bronx is not equal.
Bingo, exactly. Is not equal to mu for all. Okay, good. Okay, so now I want to compare these two. I want to test my hypothesis. So what kind of test am I going to do here? What is this? I'm comparing a sample to a known mean. That's a single sample t-test. So I'm going to say that my t-score, the t-value, the number of standard errors apart, that this mean is from that mean, that t-score is going to be equal to the difference between the two means, x bar minus mu for all, right, over the standard error. Okay, and what is the standard error in this case? In this case, we're saying the standard error is equal to 5. So the standard error, right, the standard error, I'm shooting standard deviation equal to 5, sample size 25. Standard error, once again, is going to be equal to 1. Okay, well, you know, I'm really not using the t-score here, am I, for this comparison? I'm using the z-score, right? In order for me to reject the null hypothesis, how far apart do they have to be? What does the z-score have to exceed? In 1.96, they have to be at least that far apart for me to say that the two means of the populations are different. So let's test that here. So x bar minus mu is 6 minus 4 is 2 over the standard error is equal to 1. So our z-score is 2.00. So these are further apart than I need them to be to reject the null hypothesis. So I can reject the null hypothesis and accept the alternative hypothesis. I'm going to change one thing here. I'm going to say that that standard deviation that we used didn't come from the population. That standard deviation came from our sample of 25 students. Let's do our test again. What are we doing now? That's a t-test now. Is equal to x bar minus mu for all. Oh, this is torture. Over standard error, over the standard error, right? Okay, we're going to do exactly the same thing now, except this time x bar is equal to 6 minus 4 over standard error. Standard error is going to be standard deviation, which is 5 over the square root of the sample size, which is 25. 5 over 5 is 1 over 1. So the t-score comes out to be 2.0. Okay, so now, hang on a second. Now the critical value of z, right, that we needed to exceed was 1.96. What's the critical value of t that we need to exceed? We have to go to the t-table. For what, how many degrees of freedom? 25 degrees of freedom, 24 degrees of freedom. Okay, so I lost the t-table. Let me get it back again. Okay, so let me switch to pointer and pull this up. So for 24 degrees of freedom, what does t have to be equal to? 2.064. Familiar?
Yep.
Okay. Let me get my pen back. So my critical value of t is 2.064. Hang on a second. What do we have to do in relation to the critical value of t? It has to be further out than the critical value of t, right? Our t-score is 2.0. The critical value of t that I have to exceed is 2.064, right? I have to be bigger than the critical value of t to reject it, right? And why is that? Because my level of uncertainty now tells me that two standard errors apart may not be 95%. It's less than 95% certainty. I need to be further out, right, in my interval, right? So since the critical value of t that I need for this sample size, right, is 2.064, and the actual distance between these two is only 2.00 standard errors apart, I fail to reject my null hypothesis. When I did it before with C, I could reject my null hypothesis because I was able to exceed my, I was in T critical. Exactly. Let me change one more thing on here. I'm going to do a sample size of 100. So now instead it's a sample size of 100, still standard deviation is equal to 5, right? So it's going to be equal to, again, nothing changed. The means are the same. 6 minus 4, right, which is 2, over my standard error. What is my standard error now? My standard error is equal to, it's still t because it's standard deviation. My standard error is equal to 5 over the square root of 100, which is 10, is equal to 0.5. Right? So I'm dividing 2 by 0.5. What is 2 divided by 0.5? It's equal to 4. Right? The sample size is 100. What's my critical value for a sample size of 100? I'm going to go here. I'm going to pull this up. And that's a big sample, right? So we know it's going to be 1.9, yeah, 1.984, right? So our critical value is 1.984. And what is our actual value of t? So what can I do? Critical value, t critical, is 1.98, right? And the t we calculated was 4 standard errors apart, right? So have I exceeded t critical? 4 is bigger than 1.98.
Oh, yeah.
I have exceeded it, right? So what can I do? I can reject my null hypothesis and accept my alternative hypothesis. So what happened here? What made me succeed here and what made me fail here? Well, when I knew the standard deviation of the population, I didn't have to guess at the standard deviation. I knew it, so I could use the z-score, which was 1.96. So that's the closest they're ever going to be together for 5% alpha, right? So that allowed me to reject the null hypothesis. The only thing I changed was I said the standard deviation was equal to 5 instead of sigma is equal to 5. So then I had to use the t-score. So now the t-score meant that I had to exceed 2.064. And since I didn't exceed 2.064, I failed to reject the null hypothesis. Now I increased my sample size. Increasing my sample size made my standard error smaller. So it made my t-score for the difference between those two means big enough that now I exceeded the critical value and I could reject the null hypothesis. Okay? So how do I do this now that, how do I do this? Is there another way for me to do this whole thing? Well, yes. And one of the other ways that you have to be able to do this whole thing in real life is that you can, for instance, I'm going to take the numbers that we were working with before, if I can find them again. I closed that. Okay, too bad. What we'll be able to do, what we're going to work on next week, is we will do this by hand, and then we will also do this using SPSS. And I'm just going to, oh God, apparently there was some sort of issue with some confusion about the number of licenses and the number of months that the license was going to be good for, and they've been working on trying to get it straightened out with IBM forever. But that's apparently what's going on, is that that IBM somehow or other mixed up the number of licenses and the that they were supposed to be able to have for students. And let me just open SPSS so you can see it. You, and then we'll all bail out of here. Have a good weekend. I need to get back here. Oh my goodness, I can't go to applications. IBM. I have 26, which I downloaded from their site, from the school here, thinking I'll be able to install it, but they don't have they have the license issue. So I have 25 and 26 on here at the same time. And now if I just double click a file, it opens the wrong one, which I don't have the license for. So I have to go dig it out in here to make sure the right version opens up. And I just want to show you quickly. Open up quick. These people want to go home. Here we go. Okay. I don't need this. I'm just going to throw a bunch of numbers in here. Oops, that one was too much. Okay, so there's 10 numbers I put in here. I can go up to analyze. I can go into compare means. And I'm going to go to one sample t-test. Actually, before I do that, I'm going to find out what the mean is. Yeah, I'm just going to do that, find out what the mean is. And the mean comes out to be standard deviation of 9 and a mean of 32. Okay, I'm going to go into analyze. 9.3, that's going to be 3. I'm going to go into compare means, single sample, one sample t-test. And in the one sample t-test, I'm going to take my sample, which is that I didn't name it, so it uses that name. And I'm going to compare it to a known mean of, let's see, what did I say the mean was? 30 something?
32.
32. I'm going to compare it to a known mean of 40. Okay, and I'm going to go ahead and ask it to calculate the t-value for this. And here it is, it calculated the t-value. The t-value came out to be 2.8, okay, for 9 degrees of freedom. If I went to the t-table, I could look up the t-table and I would see the critical value of t for 9 degrees of freedom, sample size of 10, 9 degrees of freedom, is 2.25, let's say. Remember, it was 2.2 for 10 degrees of freedom, maybe 2.25, right? 2.25. What did t come out to be? 2.8. 2.8 is larger than 2.25. I've exceeded the critical value of t, so I can reject my null hypothesis that the two means are the same, and accept my alternative that the two means are different, right? Well, you want to know something? It says 2.8 here, but it doesn't tell you right here, what the critical value is. So do we need to go to a table to look that up? Or maybe they give us another way to figure this out. If you look over here to two-sided significance, that stands for two-sided two-tailed test. It has a number here, which is 0.021. What SPSS does is it calculates not just whether or not what the t-value is, but it calculates the probability you would be wrong if you reject the null hypothesis. So in other words, if you are right on the cusp of rejecting the null hypothesis, what's the probability you would be wrong? 5%, right? If you exceed it, you're less than 5% chance of being wrong. If you don't exceed it, there's more than 5% chance of being wrong, so you don't reject the null hypothesis. This actually tells you what the probability of being wrong is, 0.02, 2% chance of being wrong. that means you can reject the null hypothesis. Well, we knew that anyway, because the 2.8 is bigger than T critical, so we knew it from the table, but this actually gives you the probability. Technically, it's not really the probability of being wrong. It's really the probability that you would get that big a difference in the two means if the null hypothesis were true, right? So there's only a 2% chance you would get that big a difference if the null hypothesis were true, right? So in that case, I say I can reject the null hypothesis. There's less than 5% chance of getting that extreme a difference. That's a little bit different than saying that there's a 2% chance of being wrong. I like to suggest that to students because it makes it a little easier to understand. But if you ever talk to a real statistician, it's never say that. Okay. But you understand that that's what's going on here, that like the chances that we would get that big a difference if the null hypothesis was true is only 2%, right? That they would be that far apart. Okay. So how quick was that to do compared to? There you go. Okay. That's why we love SPSS and why we're gonna bite the bullet and spend the $35 and get a copy of it. And starting next week, we're really gonna dig into it. Okay, guys? Good. Thanks for hanging in so late.